Welcome to The Explainer. Today, we are diving into a fundamental law of the universe, one that helps us find perfect, predictable order hidden inside of what looks like complete chaos. You know, it's a concept that powers so much of our modern world, and it really all comes down to the magic of averages.
Okay, so let's start with a little mystery. We live in a world that is just filled with randomness, right? I mean, the outcome of a single coin flip, the exact number of cars that'll pass your house in the next minute, these things are by themselves totally unpredictable. And yet, if we kind of zoom out and look at the averages of these random events across big groups, these incredibly predictable patterns start to show up.
So how do we do that? How do we get from all these random individual events to these predictable group outcomes? Well, it turns out there's a statistical superpower that lets us do exactly that, and it's called the central limit theorem. Okay, let's really get into it. The central limit theorem, or CLT for short, is basically the secret behind how statisticians and data scientists can make really confident predictions about, well, everything, from election outcomes to how effective a new medicine might be, and they do it all just by looking at samples of data.
So, what does this theorem actually do? Well, in short, it performs a kind of statistical magic. It tells us that something predictable, something organized, is hiding just beneath the surface of all that randomness we see every day.
Now, the key to this whole thing, the real power of the theorem, is in that last little phrase, regardless of the population's original distribution. This part is so amazing. It literally doesn't matter if the original data is lopsided or totally random or follows some kind of bizarre pattern. The averages of its samples will almost always form a neat, tidy, and totally predictable shape.
And the process is what makes it work. So, imagine this. You roll 5 dice, and you calculate their average value. That one average, that's a single data point. Now, imagine doing that again, and again, and again, maybe 1,000 times over. If you were to plot all 1,000 of those average rolls, they would start to form a very specific, very predictable shape.
And this is the pattern you get, the famous bell curve, also known as a normal distribution. This shape is super special because it's perfectly symmetrical and predictable. You can see most of the values are clustered right there in the center, with fewer and fewer values the further you get from the middle. And because we understand this shape so well, we can use it to make some incredibly precise predictions. All right, so the CLT actually has two sides to it. It doesn't just work for the averages of samples, it also works for their sums, or totals. And this is a really key distinction, depending on the type of question you're trying to answer.
So while you get that same predictable bell curve in both cases, the numbers you're working with are different. Just think of it this way. Are you asking about the average weight of one person in an elevator or the total weight of all the people that the elevator needs to lift? See? One's about an average, the other's about a sum. The great thing is, the CLT can handle both.
And this brings us to probably the most practical and crucial question, especially if you're taking a stats class right now. When should you actually use this theorem?
This right here is the golden rule. When you're looking at a problem, this is the very first question you need to ask yourself. Am I being asked about a mean, or am I being asked about a sum? Because that one decision dictates everything else you're going to do. Okay, and here's the big disclaimer, the really crucial point. If the question is about a single person, or one item, or an individual score, like what's the probability that one student has a certain test score, the CLT does not apply. The central limit theorem is only for groups, for means, or for sums. This table breaks it down perfectly. This is your cheat sheet. If the question involves an average, you use the CLT for means. If it's about a sum or a total, you use the CLT for sums. And if the question is just about one single person or one item, you don't use the CLT at all. It's really that simple. For instance, check out this study on student stress. A question about the mean score for a sample of 75 students, that's a perfect use case for the CLT. Notice the question isn't about one student's stress. It's about the average of the whole group.
So why is this one theorem so fundamental? Why do we care so much about it? Well, because it's pretty much the bedrock that so much of modern data analysis is built on.
I mean, essentially, the CLT is the engine that drives so many of the statistical tools we rely on every single day. It's what lets a company test a new website feature on a small group of users and know how it'll probably perform for everybody. It's how scientists can run a clinical trial on a few hundred people and make a really confident judgment about a drug's effectiveness for millions.
The central limit theorem also gives us this beautiful explanation for another huge idea in stats, the law of large numbers. The CLT shows us why bigger samples give you better estimates. As your sample size gets bigger and bigger, that bell curve of possible averages gets narrower and taller, squeezing itself tighter and tighter right around the true population average. It's pretty cool.
So to sum it all up, the central limit theorem is our indispensable tool. It lets us find a predictable, useful, normal pattern that's hiding in the averages of our samples, no matter how messy or how random the original data might be.
Ultimately, that's the power of statistics, isn't it? It gives us a lens to find the simple, elegant order that's hidden just beneath the chaos of the world. The central limit theorem isn't just a formula. It's a reminder that even in all that randomness, there are patterns just waiting to be found. So, what will we discover next?